My mistake last week was not bringing a road up with me, which I haven't this week.
Any homework from last week?
That which we'll think.
Did you do anything? Yes. What did you get? 40 for business customers?
Yeah.
And then 110 you can sell to leisure. Is that right? Because there were 150 altogether. Yeah, that's correct. Well done. How much did you get?
Speak 0.
40.
Great.
Okay. Question was this, as you might know.
I just have to write it down this time.
So that's it. And the answer is this. Since you've not done it, I'm not assuming. So one of you did it and got it right, and the others didn't do it. I'm assuming there are no questions.
Yeah.
Okay, so let's move on to the other thing. What did I say the other model was on? Working on. How is it? That's your first slide. I have no comments.
Next one. Yeah.
Any questions? I'm not going to read slides because students complain about lecturers reading slides.
Watching a video of you reading the slide.
Yeah, exactly.
So what if there is a shortage of seats? What do we do?
Yeah.
I'll do that thing where they keep people off planes.
So what do you do? Anybody experienced
Do
an overbooked flight?
no.
No?
I always get priority boarding.
You always get priority boarding. Why is that?
Well, then that's what people do. They don't want to lose their seat.
Yeah, exactly.
They pay a little bit extra.
Well, they would. Typically, they ask people first if they are willing to take a later flight for a compensation.
What if you say no?
That's what it's starting.
Yeah, they can say, if it's an evening flight, they say, oh, how about we give you a fancy hotel at the airport, 300 euros to vouchers for your next flight, and you fly tomorrow morning, you know. Yeah, but they're very reluctant to give you cash. But,
Sounds about right, doesn't it?
and if there are not enough volunteers, then they just bump somebody off the flight. Hopefully they realise, like Continental, that they have to do it before they actually board the flight and not drag them out once they're in their seats. But, most of the time they actually do, so they don't print you a boarding pass before they're certain that they have enough seats correctly, and they just mess up.
Will we account into the problem, or is that just the shortage of seats as a shortage of seats?
Sorry?
So if we offer compensation, surely we should put that into the problem because it'll count as a cost.
Yeah. Okay. So yes.
Two steps ahead.
First time ever.
That's right. So what you put into the model is how much you think it costs you when somebody doesn't turn up, and it's it could be all these things. So you're paying them something, but then also they'll stop liking you, and if you do it in the wrong way, then you're losing a lot of money because there's bad publicity and things like that. So of course money you have to pay the people directly because of some EU laws. That's clear how much it costs you. But if you give them, I don't know, £100 or £200 as a voucher, what's the actual cost? Because this may induce them to buy a flight that's more expensive than that, which they otherwise wouldn't. So you have to, you just have to guess what you think it costs you. Typically, if you give them a £200 voucher, you don't think it actually costs you £200 because of these things. Because they have to spend it with you. So they might even, it usually has a validity, like 1 or 2 years. Might even just not use it.
Yeah, and they don't give you the cash.
Things like that. So it's not as expensive as giving cash to people. Lots of goodwill is very hard to judge how much it is. Okay, so what you do is you estimate how much it costs you every one customer, and that's what you put into the model. And of course, it's better to have an estimate than to have nothing. That's why that's true in all over operational research. You hardly ever come across exact data how much it's costing you. So it's usually estimates, particularly when you're planning the future. Just relying on your statisticians to give you some data that they think
the government researchers aren't very good because they always underestimate everything.
Okay, so the assumptions for the simple model that we're doing is that there's a fixed number of seats. Okay, that is satisfied typically. There's only one class of customers, so we're not doing different prices for different seats in this model. And then, of course, it all gets much more complicated if you do the other things as well. What we're also assuming is that the travelers are independent, so you don't get groups. Okay.
It's not like everyone is an individual.
Customers make independent reservations, which means no groups.
Yeah.
You have to kick off the whole family.
Yeah, you can't just kick off half a family.
Yeah.
No. But also,
Yeah,
on the other hand,
Uh-uh.
on the other hand, when you have a family or a group of girls going on a hen night or something like that, then because we'll be assuming that the event that a particular customer turns up is independent of all the other customers. But when you have a family, it's not, because
they show up as a group.
More often than not, the whole family has an emergency. So sometimes it's just one member that doesn't turn up. That's possible, but sometimes and things like that. So what we're assuming to be able to analyze it is that everybody is independent of everybody else. Hush. What else have we got here? Oh yeah, so this is independently of each other. There is a fixed probability for every single person who bought a ticket that they turn up. Yeah, I'll call it P. I think I call it P.
I just like to think probability is bull, because I checked the word this morning. It said there was 10% chance of rain.
Did you miss a zero?
Well, it was raining, wasn't it?
Yeah.
Oh, shame.
So it's 100% chance of raining. Okay, so there is a fixed revenue obtained for each reservation that is accepted. So that comes from, I'll call it R. It's R. And there is a fixed shortage cost, which is what we talked about before. The kind of aggregation of all the little costs, estimated how much it hurts you when somebody can't take the seat. And I also use capital L for the number of seats available. Okay, so we've got these 4 parameters, and the rest is loss. Okay, any questions about this? Good. Oh, good. So This slide is called the model. So we have the 4 parameters that I just talked about. It was the probability, it was the size of the plane or whatever, it was the revenue from each accepted reservation, and the shortage cost. Come on, it's like in kindergarten. And then there's one decision variable. What is it?
How much to overbook? Right?
Yeah, it could be how much to overbook. It'd be more convenient, I think, to put the total number of tickets sold. So put it as number of reservations to accept. So then that means that n minus L is the number of, is how much to overbook, as you said.
Yeah.
Where also we'll be using in the model is the total number of reservations that we should sell. Okay, so what do we have? We have the demand, which depends on the number of reservations we've sold, does it not? And that's a random variable because we're assuming that people are turning up with a certain probability. What is its distribution?
Let's go with the next one.
It's certainly not exponential. Okay, so you have n customers, each of them turns up with probability p independently of everybody else. What's that distribution called? How many turn up? Yes, binomial. And there are n experiments, and each of them is successful with probability p.
College, we all know it from PMP, the British Nazi College.
Okay, so they yeah, I don't know. We don't really need this. What am I doing? I don't know what I'm doing. Okay, that's one thing. And we have another random variable, which is unsatisfied demand. Okay, that's also a random variable, which I call u, and also depends on n, and it is equal to well, it's 0 if the demand is no more than n, and it is dn take n otherwise.
Just go with the one is wrong. Good.
Oh, sorry. What's wrong? something's wrong there.
Is it just less than?
That makes no difference.
On the bottom, I still see.
Because for n it's both are 0, but
True.
well, this is always true, so there's
Yeah.
something, yeah. So why would I write it like this? I mean, sometimes there is unsatisfied demand, isn't there? So there's something wrong there. So it actually is the demand, so the people who turn up, minus the how many things we have rather than how many things we sold. So that's the problem. So both here and there, we should have L. Okay. So that's this, and now we have another random variable, the third one, which is the profit. Who likes random variables? You don't.
Because they're usually associated with
Oh, they're always associated with probability.
Should have taken stats.
stuff into everything.
So the profit is how much we earn. How much do we earn? Well, we sell n tickets, and each of them earns us R money.
Yes.
Okay, and the cost was well, each of those guys who is unhappy costs us S on average, and or you know that's what we're assuming, and there's U of n of them. So what we want is the objective is to maximize expected profit. Which is n times R minus S times the expected number of unsatisfied demands. Okay, so this is the unsatisfied demand. What else do we want? No, is that what I want to keep there? No. Okay, so yeah, so what we did last week, I think, as well, was this kind of marginal analysis. Okay, so that means that we look at what do we look at? We look at if we sell n plus 1 of the tickets, and if we sell just n tickets. So obviously, this difference is going to decrease. So with every, well, it's going to decrease provided that, what we're assuming is that this cost is larger than this one, this revenue. Okay. And then is going to go down as we keep selling more and more tickets. The profit that we get from each extra one is going to decrease because this is going to go up at some point. The cost of guys who have to bump in expectation is going to be larger than the revenue we get from the extra reservations sold. Okay. So what we're looking for is we want this to be positive. But we want the largest n for which this is still positive, and if we sold one more over that, then we'd already get the extra profit would be negative, so we shouldn't do it. Okay, that's how we analyze it. So now it's all a matter of finding out what this is, and this is so what is it? So each of them looks like this, except one of them is n plus 1 and the other is n. Okay. So when you look at that bit, what you're going to get is n plus 1r minus n r. Okay. That's the difference in the first term here. And then children's r. Or rather here on the perspective. So this is just r. Well, that's kind of obvious. That's the extra money we get by selling the extra reservation. But we have to look at the cost, okay? And the cost we get by looking at what the expected value of bumped customers is when we sell n plus 1 tickets, take away what's the expected number of bumped customers when we only sell n tickets. The bracket missing. Okay. Someone's watching. Hello. Okay. So this is easy. This is just R. Now, what is this? Okay, so as a mental exercise, as a warm-up to actually, so when I look at the demand, expected demand when I sell n plus 1, take away the expected demand when I only sell n. What is that going to be? Okay, so yeah, so one way to work it out is, as you're saying, this is just n plus 1 times p, because we know that it's a binomial distribution. And this is just NP. So when you work it out, you get P. Okay. Another way to look at it is we've got all these possible customers, and in the first case there are n of them, and in the second case there are n plus of them, and just one. Okay. Now this guy turns up, this guy turns up, this guy doesn't. Yes, yes, no, yes, yes. Okay. And for every possible outcome like this, I have two different outcomes in the second one. Okay, because let's say that these customers all do the same thing as before, and I have this extra experiment here, and that either is successful or not. And if it's not successful, then it's not adding anything. If it is successful, then it's adding one. And the probability that it's adding one is P. So the difference between the expectations has to be P. With probability P, it's adding one, and with probability 1 minus P, it's not adding anything. Now, the non-warm-up is a bit harder as well, but only marginally. Okay, so in the non-warm-up, when I'm looking at what am I looking at? The unsatisfied. I can't write the letter E properly today. The unsatisfied, probably not just today. The unsatisfied demand, when I sell n-1, take away the unsatisfied demand when I take n. Okay, I can do the same trick. And it's either 0 or it's 1. Okay. But it's only adding 1 when it does. When it does. Yeah, it's only adding 1 when this guy turns up. And this has already sold out everything. Okay. So it's not with probability P that I'm adding 1, but it's with probability that this guy turns up and that this has already sold everything. I'm adding 1. Okay, so it's not going to be P, but instead it's going to be P times the probability that I already sold out everything at that, which is the probability that the demand of n was already at least as much as the number of seats available. Yeah, is that clear? Mm-hmm. Kind of. Makes sense. Harry doesn't seem to know. All right. So now the rest is, yes. So what we have is, where did we end? Well, we're looking at this change. We want that to be positive. So this, I'll call it symbol. Now, that first thing we said was R, and the second thing, R, and the second thing is S times P times the probability that Dn is greater than or equal to L. On the far left, on the bottom line, that's the same thing as this. You don't need to know what it is. You just need to know that that's like a teleport.
Sounds like ball.
Oh, I'll do this too.
A very common mathematical tool. It's called a teleport. Start writing something, and then you have to do something else. So you make a sign, and then you make the same sign and continue. Does Killian do it a lot? Yeah.
Yes.
Because it's like teleport.
I think it's just because of the rambling and you're like, oh.
No, the arrows, you know,
Those
if
do
you
it.
make an arrow,
I'm never
then
getting it.
where do you put, well, how do you lead the arrow? It's going to destroy it. You just make a teleport much easier than if you make a railway.
So do
You
that
also
horrible
like
arrow.
numbering them.
Yeah, but I only have. Okay.
Teleport one. Just need to know it's connected, right? You might go to the wrong
So,
place.
what have we got? Oh, so we, okay, so now I suspect you have to remember this because I need to create a new page.
I wrote it down. It's fine.
I want to know the person watching this.
It says 2 viewers.
Yeah, no.
Oh, are you watching it as well?
Yeah.
Oh, so you're
It
one.
was
Speak
3 a
now
second.
or
Oh no, it's now.
forever.
Now it's 3. Oh no, I think it's just my phone.
Can you also go on the chat there?
Yeah, we
Are they saying anything?
Yeah,
Well,
those two
just-
are.
Is it you watching it and you?
No, mine wasn't registered because I was turned
No.
off. Does it say
It
3?
did say 3 when you were watching it before. And
Says
then it
2
went back
now.
down to 2.
Well, it says 2 and my phone's on it, so. Draining my battery.
I've got my kids to work with.
Maybe it's Norman.
I know them.
He's trying to see. Okay, so where were we?
What I'll do is I'll
Luckily-
pause it on the screen when it catches up.
So we wanted
Ta-da.
the largest n such that, and we had a formula which, if you,
Oh no. 26 seconds.
so that r minus sp times that probability was supposed to be positive, which says that r has to be larger than sp times that probability that dn is greater than or equal to l. Okay, which is IE is the English abbreviation for which is R divided by SP should be greater than the probability that.
Yeah, you can't see what you're doing.
Yeah, but I can see it. DN is
I hope no one's watching.
greater
It'll be
than.
good 3 minutes of blank screen.
You've just joined now. Jan is writing something. We just can't see it.
Hey, there it is. Oh no, my phone's cold. That's because I didn't pause. Oh no, it's cold. That's not the point. Yeah, I can see it now. For no reason.
It's saying low video bandwidth, which means that university internet connections
Well,
poor. Okay,
it's also to do with the fact that your frame rate is different to the frame rate of that. So you can just see the red, green, and blue lines of the screen.
very nice. Okay, well, it's not so bad when the frame rate used to be,
Jordan's commented.
but he can still read it, so that's fine.
So he's actually here. He's watching.
He
At least
actually-
he's doing the right thing. He's
He actually
watching.
messaged, I'm here.
Oh, that's good. Okay, keep watching and paying attention. Jordan, are you coming to the project meeting today? Or are we talking on Friday instead? I'm saying, I could probably bring it up, I don't know.
Surely this counts as attendance.
Yeah. Does it count as attendance, you think?
Might not have the sound on. Also why.
Okay. We've got this.
He's just gone. That's possible. That's Snapchat. Someone's supposed to catch up.
So we want this. Okay. what we're going to do now is the usual trick, which is approximation of the binomial distribution with the normal distribution. So if n and L is large, well, they kind of depend on each other. You certainly want to sell at least L, and then you might overbook a little bit. So n is large whenever L is large. I'm not sure what is the right thing. I should probably be reading it. We approximate the binomial distribution. So we can say that the dn has the normal distribution with the same mean and the same variance. What's the variance of the normal distribution? Of the binomial distribution?
NP. Oh, 1 minus P.
Yeah, that's better.
It's
NP,
usually
1 minus
Q.
P.
I remember it is.
Yeah, it's Q, but no need for another letter now.
Wow. I was there like, the expected squared minus the expected, and I had to like properly think about it.
Yeah, well, that's the definition, but with binomial, you probably remember it as a fact and don't have to derive it every time you need it, which you could do, of course. Okay, and then we approximate, then find n, because now, which is going to be fractional, such that the probability of dn being greater than or equal to L is exactly, because now we can find it exactly. So the advantage of the approximation is that we can actually calculate this value, look at the tables, find the cumulative distribution function. When is it equal to this? And then just use it. Any questions about the model?
Got any questions?
No,
He
we
said
still
yes,
haven't.
he's going to the project.
Okay, great.
We asked him in the chat.
Yeah, I don't think we can hear us now.
Maybe not.
We can't find him.
Yeah, then we have to round up or down, and I can't remember which one.
Business travel itself.
But I think you have to round up. Last time we were rounding down. Now we want to round up.
300. We're classing the 300 as the revenue. And then all of the costs are nothing.
So what does this mean for us? L is 150. R is 300. P is 0.8.
So that's sneaky.
What is?
When they pay for the flight, give you a voucher for a future flight, can you then also give you an additional 500 if there's something of loss of goodwill?
But surely, if you've already given a voucher to come to a future flight, you haven't got a choice but to come to you.
That's when they have.
Okay, so what they it's costing them £1,000 altogether. We can deduce from this information. So this is 1,000. Is it going to fit here? Probably not.
Yeah.
Nah. Can you see what I'm writing? Actually,
That's an amazing dot in the middle of
yes,
it.
when you couldn't see it. Okay, so we have all these things. So what are we looking for? We want the probability that the demand n is greater than or equal to 150, which was L, should be equal to R divided by SP. So the revenue was 300 and S was 1,000 and that was 0.8. And so 3 divided by 8 is, what do you know? I don't actually remember that.
Well, 1/8.
That's okay, so it's 0.375. So now what happens is so what's the distribution of this? Well, we're approximating it with the normal distribution. What is the mean? 0.8 times n. And 0.16 n apparently should be the variance. So now you go to the tables of the thing. What'd you get?
No, just with my 1.16.
Tables. You get that the probability of the normal of the standardized, what's it called, standard normal distribution. I get this value from the table, 0.32. That's 0.375, something like that. So from this, you get that in the table. And now, how does it work? So now, you want that 0.32 should be 150 minus our mean divided by our standard deviation. Because this times sigma plus u, which is 150, take away 0.8n times 0.4 root n. And from this, we get that. This is the same. Well, this implies that 0.8 n, 0.128 root n t should be equal to 0. Yeah, doesn't make sense. So it's still not quite so easy because you get the number, but what you actually don't know. You know the number, what you're trying to do is like this, but you don't know the distribution because you don't know the n. That's actually what you're looking for. So if you're assuming that if normal distribution with some cancers, you need to find out. You've got those parameters in terms of n. So when you do this, you get something for the standard normal distribution, which gives you something which leads to a quadratic equation. Recognize this as a quadratic equation, or a quadratic equation in root n. And so from this, when you solve this. Have you solved it on the thing?
No, you want it in the root.
Have you solved it?
No.
0.8 times 185. I don't know. Well, what it's giving me is n equals 184.96. But maybe, okay, I'll check this, fix it. Or maybe this is it. So the conclusion so in this case, the model tells us to round up because if you remember, we were looking at n plus 1, profit for n plus 1, take away the profit for n, and that was supposed to be positive. In fact, we were going to sell n plus 1 reservations. When you get a fractional n, you get something between n and plus 1. So up to 184, you're still increasing your profit. And then from this number on, you're no longer increasing your profit, but you're still willing to sell that one extra seat. Okay, so round up. And conclusion is to sell 185 reservations. That's an example of that. But it's still some work, and it's not immediate from adding RS and P.
So we find it's different.
Okay, any questions? Not, then there's another exercise on similar
we covered it next week.
In the handout, and in the middle, hopefully. That's it.
Hopefully Friday.